Okay, we are going to have a intro video here on torque, and a couple of different ways we can get into it. Kind of the classic way to think about torque is you've got a bolt and you're trying to undo the bolt, and you get a wrench, and then you're applying a twisting force with the wrench. So that's kind of the idea behind a torque. It's a force that is going to result in something moving in a rotational way. And we can talk about a couple different things, like how a smaller wrench is harder to use than a bigger wrench, and kind of understand the idea behind that as well. So one way to get into it, to think about it just in terms of how we can define torque, is by doing what we've done before and taking one of our translational equations and turning it into a rotational sense. So if we think about the linear force, the analog to that is going to be torque, and we're going to write that as a lowercase tau, and we're going to try to see what it actually makes up over here. Well, our rotational equivalent of mass is, of course, moment of inertia, and our rotational equivalent of acceleration is angular acceleration, like that. So this is torque is moment of inertia times angular acceleration. It's like F equals ma, and we can solve problems once again by knowing what the torque is and what the moment of inertia of an object is, and you can figure out what the acceleration is going to be, and other problems like that as well. If we kind of dive into the units for a moment here, the units, we can actually figure something out to help us get another sort of definition for what torque is going to be. So if we look at the units over here, the units for I are kilograms meters squared, and the units for alpha are radians, which is just like one per second squared. So when we combine those together, our torque units turn out to be kilograms meters squared per second squared, which strangely enough is the same units as joules, but we're not really talking about energy here. We're talking about something else. So we can actually split this up. Now, why you would do this, I'm not sure exactly why you would do this, but we could split this up into kilograms meters per second squared times meters. And now you can see what we're getting inside of here. These are units of force, and then these are units of distance. So if you multiply a force times a distance, you can get a torque. Same thing for joules, by the way. If it's a force times a distance, you'll get joules. But in terms of torque, here's what we mean by that. So I'm going to just draw there's the bolt that we're trying to get out. Good. And then, I'm always really bad at this. Here's me trying to draw the wrench. It's actually not so bad. Okay, good. It's not too great, but anyways, there's the wrench that we're trying to do. Good, little hole in the end like that. So what we're talking about with this force times distance is we're going to apply a force to the wrench over here, force like that, and then the distance is going to be the distance from the center, the pivot point, out to where you applied the force. And rather than calling it a distance, we're actually going to call it a radius r, like that. So what we're going to get is another side definition for torque, where torque is going to be the radius times the force, like that. So how far away you are times how much force you put on it. And what this is showing us is that the bigger the radius is, the more torque that it is. So if you have a smaller wrench like this, you won't be able to get as much torque because I don't have as big of a radius as this bigger wrench over here, where I'll be able to get more torque because I can get my radius a little bit further away like that. So now there's a little bit of an issue with this equation over here because it's not really complete, because these things are actually vectors. So force is a vector, radius is actually a vector, which is sort of strange, but we're going to take the radius as starting here and going this way. So the direction of this r is going to be starting there and going that way. So the radius is going this way and the force is going this way. And when you multiply two vectors together, you have a little bit of a choice for about whether you put a dot product in there or whether you put a cross product in there. And the difference is that the dot product is going to go by the cosine of the angle between them. We usually do that. That's a little out of focus. Let's see if I can get this more focused. There we go. And then the cross product is going to go by the sine of the angle between them. So let's see if we can reason whether it's better to go by the cosine or the sine. So what we can say is, in this particular situation, I have my force that's going perpendicular to my radius, so my angle right there is going to be 90 degrees. And If I did the cosine of this, then the cosine of 90 is going to give me 0, and I would get 0 torque in this situation. If I did the sine of it, the sine is going to give me 1, and this is going to kind of be a maximum torque. The other way we could think about it is if I put my force and my radius in the same direction. So if my force was like this, so if I'm on my bolt right here, and I pull on the wrench that way, it's not going to turn the bolt at all. So if this were the case, if they're in the same direction and my angle were 0, then I'd get a maximum for my dot product and I'd get a minimum for my cross product. But that's not going to be the case. So this is going to be a cross product like this, which means in a cross product, the thing, you multiply two vectors together and you get a vector out. So torque is actually going to be a vector, which is going to be pretty interesting. So what's going to be the direction of this vector? So the direction of the vector is the cross product. So we need to take your right hand, not your left hand, make sure you're taking your right hand, and you need to cross R crossed into F. So if I do R like this and then crossed into F, then my thumb is pointing down into the page right there. So once again, R cross F. I put my fingers in the direction of R and then I curl them in the direction of F, and then my thumb's going to point down into the page. So the direction of this torque right there is down and into the page, which makes sense because if I start to turn this thing, then it's going to start to get an angular velocity, and the angular velocity of this thing has a direction as well. If I curl my fingers around like this, then the angular velocity of this thing, if it starts spinning around and around, is also going to be down. So my torque turns out to be in the same direction as the angular velocity increasing, and also the angular acceleration. So that all makes sense. So it's a cross product here, and you have to remember the right-hand rule for the cross product. Okay, let's see. So, okay, let's look at a diagram from the book over here and talk a little bit more about this angle. Oh, sorry, I actually meant to inside of here, right, that if you just want the magnitude of the torque, then you're going to take the magnitude of R times the magnitude of F, and then you're going to take the sine of the angle between them. If it's 90 degrees, then your sine of 90 is 1. But for example, over here, this is a diagram that's straight from the book. This says the torque due to the tangential component of the force causes an angular acceleration around the rotation axis. So what do we have here? We have a rod with a mass on it, and this time the force is not at 90 degrees. So here's our force, here's our radius, and if we want to try to find the torque, what we need to do is we need to find this component of the force right there. So that's the tangential component of the force. It's really going by the sine of this angle right there. So there's the angle between them. I guess I should mention that's a little bit tricky. Because this is R cross F, we need to sort of pay attention to the angle between them. And the angle between them is not this angle, but it's this angle over here. So here's my R. There's my R vector like this. And my force vector would be like that. And then the angle between them is right there. So it's a little tricky to see, but it's not this angle, it's that angle right there. And if I take the sine of this angle, is going to be related to this side of my triangle, the opposite side. So that's the tangential component of the force. So this component of the force times this radius will give me the torque, and that's going to create my rotation, angular acceleration around that rotational axis, right? So it's just kind of important to remember that the angle between these things can be a little bit deceptive, where you're going to actually put that angle. It is also important that it's R cross F and not F cross R. So the cross product is not, I don't know, what's the mathematical word, reversible? That's not the right way to put it, but it does make a difference for the order that you put it in. F cross R will give you something in the opposite direction, depending on where you do it. So over here, if it's R cross F, so here's my fingers in the direction of R, and then I curl them in the direction of F, and then this torque is going to be pointing up. If it were F cross R, then it would be down, but it's R. I start out with my fingers in the direction R, and I curl them towards F like that, and then my thumb points in the direction of the torque right there. Okay, and a couple of the diagrams in the book to just check out right here. This one says the torque due to this force causes a rotation around the axis. So my rotational axis is here, which extends towards you. Here's my force, here's this, there's the angle between them, right? So the torque is going to cause a rotation this way. If I want to figure out the magnitude of the torque, I'm going to need to find the tangential component of this force right there, right? There's a second part to this diagram here. That's what it says. Only the tangential component of the force causes the rotation. So we're taking that tangential component. Although it also says over here, you can calculate the same torque by using what's called a moment arm and a line of action. So if I take my force and I extend the line of action of my force, and I just extend this backwards this way. Okay, so I extend this backwards this way over here. Then I connect at a right angle a line over here. Then this says R perpendicular right there. So that's like the perpendicular component of the radius, which is also, that angle is the same as that angle. So this is also the sine of this angle. So you can call this what's called the moment arm right there. So it's called the moment arm distance. So this times the force will also give you the same thing as this times this force. In a sense, it's actually kind of doing whether you want to do F times sine of theta and then multiply it times R, or whether you want to do R times sine of theta, phi, not theta, it's phi, sine of phi, and then multiply that times F. So it's the same thing. This component right here is R times the sine of this angle, and we call that a moment arm right there. So that's just something to notice. Okay, so what can we do with these torque things? Well, we can do problems where we are just spinning something around. You can have a torque on it. You can figure out the magnitude of the torque, and you can figure out the acceleration, and those problems are not too tricky to do. But what we can also do is we can actually get back to this problem over here, where you have a hanging mass, and you've got now a pulley that actually has some sort of mass on it. And this is sort of what we were doing in class with the big wooden discs, and we are accelerating the wooden discs. So now we can actually analyze this type of problem right here, and we can actually figure out some types of accelerations. So this says over here, the torque due to the cord's pull on the rim causes an angular acceleration of the disc. So what we say is that if you've got a string that's wrapped around a pulley, the string at this point right there is actually going to cause a torque on this pulley. And the torque is going to be caused by the tension in the string. So there's a tension in the string right now there. When we say the tension in the string is going to act sort of like just on this point on the pulley right there. And of course, there's a radius associated with that pulley, which is sometimes capital R if it's a set radius. So I've got a force and I've got a radius right there. Don't get confused because this T stands for tension and torque is going to be tau. So don't put capital T's for torque. So you have to use taus for your torques. But the torque on this thing right there is going to be R times T, and they're going to act at right angles to each other, so we don't have to worry about the sine of the angle between them. So we have a tension in this string, and the tension, once again, is sort of touching the pulley at this point, and it's going to apply a torque to this pulley and make it rotate around that way. So it's going to cause an angular acceleration of the disc. Of course, down here, we've also got tension pulling up there. Oops, that's a T. And we've got mg pulling down right there. So we can kind of make a setup here, and we can solve for what the acceleration of this whole system is going to be. These two forces determine the block's linear acceleration, and you can relate these two accelerations together. So let me go through a little bit of a derivation here that's going to be solving the problem that we did in class, which was the pulleys on the discs. So let me go grab one of those so we know what we're looking at. Okay, so it's not exactly the same. I can't fit the whole thing in the screen, but what we had was, of course, string that was wrapped around a much bigger wheel than this. So the string was wrapped around, and it was in the vertical direction, and then hanging from it, we had this hanging mass. So looking at it from a side view, it was like this. The string was here, the mass was here, and it was pulling and it was rotating around. So it's basically the same thing, just a little bit different. So I want to try to figure out how we can solve for the actual angular acceleration here and what that graph is going to look like. If you remember in class when we were taking some data, let's see if I can get a new piece of paper over here. I'll just do it down here. So when we were taking data in class and you made a graph and you increased the hanging mass and you were plotting for angular acceleration up here, it seemed pretty linear to start, but then once we added more and more mass, it kind of didn't really end up linear and it sort of curved around like that. So I want to actually solve this whole thing out for this rotating disk, and you can kind of see this example right here. Okay, so how are we going to do that? Let's actually just get a fresh page over here, and let's draw this out again, just sort of same diagram as we did before. So what are we going to have here? We're going to have a rotating disk like that. That was pretty terrible for a circle, but anyway, there's the center of it. It's going to have a certain radius, which is going to be r, and it's going to have a certain mass, which is going to be m. Now, of course, we could calculate the moment of inertia of the disk is going to be 1/2 mr squared. That's just something to keep in your back pocket. We're going to have a string that's attached here that's hanging down. We're going to make this hanging mass have a little m for its mass right there. And then what we're trying to do is we're trying to find the angular acceleration. And we're going to find this just in terms of variables and nothing else. So it's pretty interesting to think about how we're going to do this. First of all, what we're going to do is we're going to draw a free body diagram for this mass right here. So there's your mass m, and we've got mg going down, and we've got tension going up. We also kind of need to draw a free body diagram for the disk, but it's hard because you can't just put a dot for the disk because we need the disk to have this radius to it. So what we can kind of do is draw the disk by itself again and just note that I've got tension right there and I've got a radius right there, and that's kind of my free body diagram for a rotating thing, a tension and a radius like that. And what we've done in the past is once we've drawn free body diagrams, we write a net force equation. So we're going to write a net force equation for here. On this side, we're going to write a torque equation, and then we're going to kind of relate those together. First thing we need to do is we need to talk about the directions here. There's this saying we talked about before where they say clocks are negative. So we need to know what the direction is. So generally, we like to say that going around this way is the positive direction, which would make this way the positive direction as well. So I'm just going to stick with convention here and make counterclockwise positive, which means for this mass right here, positive is going to go up in the up direction and negative is going to go in the down direction. It's a little bit of a pain because the whole thing is going to be going this way, so maybe it would have been better for me to draw the picture with a mass on this side, so everything could have gone in the positive direction, but that's just how it goes. So what that means over here is that when I'm setting up my net force equation, I'm going to do net force is mass times acceleration. My tension is in the positive direction, so I've got T, my mg is in the negative direction, minus mg, and this is going to give me NA. Right? Okay, so that's good like that. And then what we can do over here is now we have this torque equation over on this side. So we're going to write torque net equals I alpha. Yep, net torque. We only have one torque here, so we only need to write one thing in here. You can imagine a situation where there might be multiple torques. Maybe there's another force here, or maybe someone's grabbing the disk and putting a force on it in another direction. In this case, it's easy. We just have one torque. That's all we have. So how are we going to do this? So because this tension is going in the negative direction, the net torque is going to be minus T times R, or really R times T, I guess if it's radius times force. Either way, it doesn't really matter. We don't have to worry about the direction here. I know we were talking about the cross product before and the directions, but we kind of took care of all the directions here. We don't care that the actual angle for the direction for the torque is really into the page. That's not going to really make a difference here. So that's our net torque, and then this is just I times alpha. And because we have this disk is mr squared over here, or 1/2 mr squared, we can just go ahead and write that as 1/2 mr squared times alpha. So how do we do this now? We're trying to find alpha, but we've got alpha and torque and acceleration, and they're all variables we don't know, and we only have two equations. But we can add in a third equation right here because we know that the acceleration, a linear acceleration at this point in the disk, is going to be equal to the radius of the disk times the angular acceleration of the disk. That wasn't the best alpha. Let's do a different alpha. Equally bad, but anyways, you get the idea. So I can relate together the linear acceleration of this mass with the angular acceleration of this whole system over here. I feel like we're out of focus again. There we go. So the linear acceleration of this mass, I can relate to the angular acceleration of the disk over here, through this over here. So let's just start to kind of combine some things together. What I'm going to actually do is I'm going to just start with this equation. I'm going to solve it for tension. So I'm going to write tension is ma plus mg. And then I'm going to go ahead and stick in R alpha for this A right there. So now I can get little m times R times alpha plus mg. And that's what tension equals. And now I can take that tension and I can stick it up here in this equation. So let's bring this equation down here a little bit. And then we can say, so how's this going to go? Minus T times R. So that's this. So I'm going to have R times this whole thing right here. Right? Okay, so that's going to be tricky. So let me just write this down here. Minus T times R equals, why do I have this I alpha mr squared? Oh, mr squared, this should be equal right there. I don't know why I had those things. So this is 1/2 mr squared times alpha. And now I'm going to put this in for tension right there. So I'm looking at some notes on another page, and I'm kind of doing things a little bit differently here. But I hope that this all works out. So let's see. Let's actually do this. Let's change this. First of all, that R can go away with that. Okay, that's better. So now I'm just going to write this as tension is going to be minus 1/2 big M times, oops, that's not a big M, that's a little m. Big M times R times alpha. So see what I did here? I just got rid of one of the R's and I brought the negative to the other side. So now I can relate this together with that one, and I think that that's going to be better right there. So let's do this. Now I have minus 1/2 m r alpha equals over here m r alpha plus mg. And now I only have one unknown, and that's my alpha inside of here, right? So now I can just try to do a little bit of manipulation here to get this alpha by itself. So why don't I bring this 1/2 mr alpha over to this side? So this is a big M, by the way, m r alpha. Okay, so now I can bring this over here so I can get this as 3/2 m r alpha plus mg equals 0. So now I'm solving for alpha, so I'll do 3/2. Oh my gosh, I went off the page. 3/2 m r alpha equals minus mg. And then I should be able to just do alpha equals minus 2/3, which I don't really care about. And then on the top here, I've got mg. Oh no, I did something wrong somewhere. I've made a mistake. Can you guys figure out where I made a mistake? I don't want to redo this entire video. I feel like I made a mistake somewhere, and I don't really remember where it was. I feel like, oh, you know what it was? Shoot, okay. Sorry, you all. This is totally wrong. This M right here is actually a little m, and that is taking me down into here, which is a little m. So I'm going to go back here. Sorry, this is a little m. That's why it helps to be very neat over here. So then this is wrong from here down. Okay, phew, I'm glad I realized what my mistake was. So that's a little m, and then that's a big M. Okay, so little m here, that's a big M, and that's a little m as well. Okay, so now we need to redo this. So let's just get rid of all this, and we'll bring it over here a little bit. So now I'm trying to get alpha by itself. So I'm just going to do this. I'm going to do little m times r times alpha minus a plus 1/2 big M times r times alpha equals minus mg, like that. Okay, now I'm back on track. Ooh, I got a little nervous there. Okay, so now what can I do here? I could pull an R alpha out of this. So I could pull R alpha, and this is going to be little m plus 1/2 big M, and that's going to equal minus mg. And then I can solve for alpha. So alpha is going to be minus mg over big R times m plus 1/2 m, like that. So there we go. So this is how the graph is supposed to work. Now if we actually plotted this, and we made a plot of acceleration versus little m is the hanging mass over here. Big M for us was a constant, but little m was changing. So if you plot this equation, and I'll show you in class, you actually get a graph that looks like this out of it. So this right here, because you have an m up here and an m down here that's kind of combined together with some other things. So that's going to be the graph of this thing over here. So it goes off like this. That's how this graph is going to look. Okay, phew. Glad I realized my mistake, and it's a lesson for us all to just keep track of your big M's and your little m's. So that's how we're going to deal with torques and rotating things like that. You can imagine a harder question might be something where you had a disk and you had a mass hanging on this side and you have a mass hanging on this side. Maybe this is M1, maybe this is M2. Yep, so now you've got two torques. An even harder question might be, instead of this mass hanging here, maybe you have two different radii. So you have a disk, just like we did, that's got a bigger outer disk and a smaller inner disk, and you've got another mass hanging right there. What's going to end up happening, though, is this is all going to get really, really easy when we start to consider energy. So for now, we're kind of doing the forces thing, and just like in linear motion, energy is a way easier way to go than forces. So, all right, long video, but thanks for watching.